Good morning/afternoon, everyone. Welcome to today's presentation. I'm Dr. S.K. Singh, holding a PhD in this field. Today, we'll be exploring the qualifications of the infrared Fourier transform infrared spectrophotometer. We'll discuss what it is, how it works, and its significance in analytical chemistry. I'm excited to guide you through this topic, so let's get started. Let's start by looking at the scope of what we're covering today. This applies specifically to FTIR instruments, which are used in a variety of crucial ways. For example, they help us identify raw materials, ensuring we start with the right components. They also play a key role in confirming the identity of finished products, giving us confidence in quality. Additionally, FTIR is essential for functional group analysis, helping us understand the chemical characteristics of our substances. Moving on to the objective, our main goal here is to establish documented evidence that these IR spectrophotometers are performing accurately, reproducibly, and consistently for their intended purposes. This means we want to ensure the instrument's performance is reliable over time and across different conditions. Finally, let's briefly touch on the qualification lifecycle, which is fundamental to maintaining this reliability. It starts with design qualification, or DQ, where we verify that the instrument is designed appropriately. Next is installation qualification, IQ, which confirms that the instrument has been installed correctly. Then there's operational qualification, OQ, ensuring the instrument operates as intended during normal use. And last is performance qualification, PQ, which validates that the instrument consistently produces valid results in real-world conditions. All of these steps are interconnected and vital to maintaining the integrity of our testing processes and ensuring the FTIR instrument performs optimally throughout its life cycle. Now, let's talk about the installation qualification, or IQ, which is a crucial step in ensuring our equipment is set up correctly. First, we need to verify that the instrument has been installed exactly as the manufacturer instructs. This helps us confirm that all installation steps were followed properly, setting a strong foundation for reliable operation. Next, we look at environmental conditions. The temperature should be maintained between 20 and 25 degrees Celsius, and the relative humidity should not exceed 60%. These conditions are essential to keep the instrument functioning accurately and to prevent any environmental interference. We also need to check the electrical supply and grounding. Proper grounding and stable power supply are vital to avoid electrical issues that could affect performance or damage the equipment. Another key point is verifying the software version and ensuring access control. Having the correct software version guarantees compatibility and functionality, while access controls help us maintain security and proper user management. We also examine the accessories, including the ATR crystal or KBR press, the desiccator, and the printer or computer. Confirming these are present and in good condition ensures the full system is ready for operation. Moving on to IQ acceptance, the most important part is that all these items have been verified and documented. Once verified, we mark this step as complete with a check mark, showing that everything is in place and ready for the next phase. In summary, the IQ process helps us confirm that the installation is correct, the environment is suitable, and all components are accounted for, setting the stage for consistent, reliable results in our analysis. Let's now focus on operational qualification, or OQ, which is a crucial part of validating our analytical methods. According to USP 854, there are specific parameters we need to evaluate to ensure our instruments are performing correctly. These parameters include wave number accuracy, resolution, signal-to-noise ratio, repeatability, and baseline stability. Wave number accuracy is about making sure our spectrometer is measuring the correct wave numbers, which directly impacts the precision of our results. Resolution refers to the instrument's ability to distinguish between two close-lying peaks, which is vital for accurate component identification. The signal-to-noise ratio, or SN, tells us how clear our signal is compared to the background noise. A higher SN means more reliable data. Repeatability assesses whether the instrument produces consistent results when analyzing the same sample multiple times. Lastly, baseline stability ensures that the instrument's baseline remains steady over time, preventing false or inconsistent readings. All these parameters are interconnected and essential for confirming that our instrument is performing reliably and accurately, supporting the overall integrity of our analytical process. Now, let's take a look at the standard for polystyrene film, which serves as the USB reference standard. On this slide, you'll see the key reference peaks identified in the infrared spectrum, measured in centimeters inverse, or the main peaks we focus on are at 3060, 1601, 1583, 1154, and 1028 cm. These are characteristic of the polystyrene structure and are essential for verifying the accuracy of our measurements. Moving on, we have the acceptance criteria for the wave number accuracy, which is set at plus or minus 1 cm. This means any measured peak should fall within 1 unit of the reference value to be considered acceptable. Let's see an example to clarify this. Suppose we observe a peak at 1602 cm and the reference peak is at 1601 cm. To determine if this is within our acceptable range, we subtract the reference from the observed, which gives us a difference of plus 1 cm. Since this difference is within the plus or minus 0 cm range, we can conclude that this measurement passes the accuracy test. This check is crucial to ensure our spectrometer is calibrated correctly and our data is reliable. Now, let's take a look at the resolution criteria for the OQ Test 2, which focuses on the standard polystyrene film. The key point here is that we need to ensure that the resolution between the peaks at 3060 and 3080 cm is clearly separated. This means that these two peaks should be distinguishable from each other without overlapping. Alternatively, if the instrument's specific resolution capability is taken into account, the resolution can be considered acceptable if it's less than or equal to 4 centimeters inverse. To give an example, if you observe two peaks that are distinctly resolved and separated, then you meet the resolution requirement. This is a good indicator that the test is successful and that the instrument is functioning properly. Overall, achieving proper resolution is critical because it ensures accurate identification of peaks, which is essential for reliable analysis and quality control. All right, let's walk through this example. We have a signal of 0.25 abs and a noise level of 0.0002 abs. The goal here is to determine the signal-to-noise ratio, or SN. To do that, we simply divide the signal by the noise, so 0.25 divided by 0.0002. That calculation gives us a ratio of 1250. And since 1250 is well above the acceptance criterion of 1000 to 1, this passes the test. This is part of our OQ Test 3, which focuses on the signal-to-noise ratio. The procedure involves scanning the background and the polystyrene film, then measuring the noise in a non-absorbing region, like between 2100 and 2000 cm. The key point here is that our acceptance criteria require the SN ratio to be at least 1000 to 1, or as specified by the manufacturer or USB standards. This test ensures that our instrument sensitivity is adequate for reliable measurements. Let's look at this example of peak absorbance values. We have 6 measurements: 0.521, 0.519, 0.522, 0.52, 0.521, and 0.519. The goal here is to assess the repeatability of our instrument. To do that, we first calculate the mean, which in this case is 0.52. Then we determine the standard deviation, which is 0.0012. Next, we calculate the percent relative standard deviation, or percent RSD, by dividing the standard deviation by the mean and multiplying by 100. This gives us 0.23%. Since this value is well below our acceptance criterion of 2%, we can conclude that the measurement is consistent and our instrument passes the repeatability test. Now, moving on to the procedure for the OQ Test 4, repeatability. It involves scanning the same polystyrene film 6 times without repositioning it. The key acceptance criterion here is that the percent RSD must be less than or equal to 2% for either absorbance or peak position. This ensures our method is precise and reliable over multiple measurements. So the main takeaway is that by performing these repeated scans and calculating the percent RSD, we verify that our instrument's measurements are reproducible and within acceptable limits. Now let's take a look at OQ Test 5, which focuses on baseline stability. The procedure here involves scanning the background across the full spectral range, which is from 4,000 to 400 cm. This helps us ensure that the baseline remains consistent throughout the measurement. The acceptance criteria are quite straightforward. We're looking for no significant drift in the baseline, meaning it should stay steady without any large fluctuations. Additionally, the baseline deviation should be within plus or minus 0.005 abs, which indicates high stability and precision in our measurement. The result for this test was that the baseline was stable. That's a good sign, because a stable baseline means our instrument is functioning properly and our data will be reliable. Overall, this test is crucial because it confirms that our background measurements are consistent, ensuring the quality of the spectral data we rely on for analysis. Now let's look at this PQ example. We have a sample of paracetamol, and the standard reference was measured using ATR mode. The results show a library match of 0.98, which is quite high, indicating a very close match to the reference spectrum. All the characteristic peaks are present in the sample spectrum, which is a good sign. This means the sample was correctly identified. Moving on to the purpose of performance qualification, or PQ, it's really about verifying that our process performs consistently under real-world, routine conditions. Essentially, we want to make sure everything works as expected during normal operation. The procedure involves analyzing a known reference material, so a standard sample, and then comparing its spectrum to an approved library or reference spectrum. This comparison helps confirm that our measurement system is accurate and reliable. When it comes to acceptance criteria, we're looking for a correlation coefficient of 0.95 or higher. That indicates a very strong match between the sample spectrum and the reference. Additionally, the peak positions should match those in the reference spectrum, confirming the identity of the sample. All of these points, library matching, peak presence, correlation, and peak alignment, are crucial to ensuring that our analytical process is performing correctly and consistently. Let's take a look at the frequency of qualification for different activities. First, IQ, or installation qualification, is typically performed just once, either when the equipment is installed or relocated. This helps ensure that everything is set up correctly from the start. Next, we have OQ, or operational qualification, which should be carried out annually, or more frequently if there's been a major maintenance activity. This helps us verify that the equipment continues to operate within the specified parameters over time. Then there's PQ, or performance qualification, also scheduled annually or during method verification. This step confirms that the equipment performs reliably in real-world conditions, supporting consistent quality. Finally, the polystyrene check is usually done monthly, or as specified in our standard operating procedures. Regular checks like this are crucial for maintaining ongoing quality and catching any issues early. Connecting all these points to our overall theme, consistent qualification and preventive checks are key to ensuring our equipment remains reliable, compliant, and capable of producing high-quality results over time. Let's take a look at some key reference guidelines that help shape our analytical practices. First, USB 854 covers mid-infrared spectroscopy, which is a crucial technique for identifying and quantifying compounds in our pharmaceutical analysis. It provides standardized methods to ensure consistency and reliability. Next, USB 1058 focuses on analytical instrument qualification, or AIQ. This guideline guides us through the steps to properly qualify our instruments, ensuring they perform accurately and consistently over time. It's all about maintaining trust in our data. Moving on, the European Pharmacopoeia, specifically EP2224, also offers detailed methods for spectroscopic analysis. It emphasizes method validation and proper documentation, which are vital for compliance and quality assurance. Then we have ICHQ2, R2, which is all about the validation of analytical procedures. This guideline helps us establish that our methods are suitable for their intended purpose, covering aspects like accuracy, precision, specificity, and robustness. Finally, the WHO Technical Report Series 1010 and 1033 provide international standards and recommendations for analytical method validation and instrument qualification. They help ensure that our methods are globally acceptable, fostering consistency across different regions. All these references are interconnected. They form a comprehensive framework that ensures our analytical methods are reliable, validated, and compliant with global standards. Keeping these guidelines in mind helps us maintain high quality in our pharmaceutical analysis processes. For further support, please contact us. We're here to help you with any questions or additional information you might need. Don't hesitate to reach out. We want to ensure you feel confident moving forward. Thank you very much for your time and attention today. We appreciate your engagement and look forward to supporting you in your next steps.